Yep.
Quick question.
Sure.
For the third problem on the open phone.
Mhm.
So when you try to break down those fixed walls, because you have this vertical,
Mhm.
technically you're breaking away. Let's say, for example, you want to assign your own white wall.
Mhm.
But when I put up the mesh, like the block mesh to like load it up again,
Mhm.
it won't gives me like all these errors.
Yeah.
And on you, I pretty much assign like a value to the right wall.
Yeah.
And everything else as a fixed, not fixed, no boundary condition.
Mhm.
And it still gives me like issues in my control after that.
Yeah. So the third problem, I think, is the one which is most involved because you have to do kind of two things. And so you do have to make a change to block mesh dictionary. Right? Because you basically have to make a new boundary patch definition, right? Right? Because at first you only have three, right? So you only have just the moving wall. You have fixed walls, and then the front and back, right?
Yes.
Right. And so if you want to add, like, let's say the right wall as a boundary condition, you actually need to make a new one here, right? So you can make one called the right wall, right? And then what you need to do is you need to basically take one of the faces that was under fixed walls, right? And then move that into your new boundary condition grouping there. So basically you're making a new definition, say that, we're creating this new group of faces. Well, in this case, it's just one face, and then we're going to apply the boundary condition there. And then you also need to make a change in the U file, right?
Yes.
So this is probably what you've done, right? And so now that you've created the right wall, you need to create a boundary condition here for right wall. It needs to have some velocity. So fixed value, uniform. So let's say you want to move it in the vertical direction, right? So it'd be 0, 1, 0, right?
So yeah, that's what he did.
But then you also need to make a change in the P as well, because if you're making a new boundary surface, you also need to define what the pressure boundary condition there as well. In this case, it's nothing. In this case, it's a 0 gradient, but you do need to define it, right? So in the P file, you go to make a new section called right wall. You give it, say, a 0 gradient. Yeah, so those are all the steps that you would need to take to do that part.
It gave another error. It said it's changed, or it was missing the variable under the nut one.
Ah, okay.
Yeah, that one I don't know what to do for that.
I went as far as to throw it into every single one of the subdirectories from 0.
Yeah.
And it's still giving me an error.
Oh, really? Okay. Okay.
Because mine went from the block mesh ditch, we fixed that, and after that, it gave me a control dig.
Yeah.
And so I'm just like,
They kept giving him an error message of like polymesh not calling a variable correctly.
Oh, interesting. Okay, so I think probably what you guys have to do is so I wasn't planning on doing this until the second activity, but I think you're right in that that the OpenFOAM does expect you to define the condition for every turbulence variable as well. So what you can do is you can actually change the simulation type. So if you go under momentum transport. Right, so there's a file. We didn't really do much with it, but we just kind of looked at it. So under the constant directory, there's a file called momentum transport. In there is a setting called simulation type. Exactly, yeah. So I mentioned it. It was mentioned briefly in the activity, but we didn't actually change it. But you can actually change this from, I think by default it's RAS, but then you can change it to laminar instead. Right. So I think that is in the first act. That's probably what I did in my own case. That's probably why it worked for me, because I changed it to laminar. Because then what you can do, you do have to make one more change in momentum transport. So there's like another block here for like the RAS settings, right? You can just go ahead and delete those. And so the only line that you should have in momentum transport should just be the simulation type set to laminar. And then what you can do under the zero directory, you just delete, if I can spell delete correctly. You delete all the variables that have to do with the turbulence modeling. So delete everything except U and P. Yeah, because when you're running with an RAS, it's going to expect those turbulence variables. But if you change it to laminar, you can just get rid of them, and then that'll make things a bit easier. Yeah. Yeah, I've kind of changed my mind a little bit. I wanted to get into the turbulence modeling stuff after the spring break, but it was basically a decision between turbulence modeling and time stepping. So we're gonna do time stepping instead. So basically for the rest of the class, we're gonna run the math. So,
Okay.
yeah, give that a try for that problem. I think probably what I'll do is that I'll probably send an email to everyone to say that problem changing boundary conditions. We'll talk more about an activity 2. So that one will be probably optional because I think probably everyone's probably struggling with that one. But if you want to get that one to work, this is the steps that you have to do. Yeah.
Thank you.
Mhm. Problem 4 you should be able to do, just because problem 4 you just change the locations of the vertices. Yeah, but the boundary conditions don't change for that. So yeah. Yeah. Although another easy way you could do problem 3 is that you can basically take one of the you can take the bottom surface and add it to the moving wall, right? So basically take that base. So the other boundary conditions don't change. You're just moving the top and bottom wall with the same velocity. So that would work in this case without having to change any of that stuff there too. So that's another way you can do it. But I think I think we'll just make it optional, and we'll talk about it more in activity 2 after spring break. Yeah.
Thank you.
Yeah.
Okay. All right. So it is 4 o'clock. So let's go ahead and get started. All right. Good afternoon, everyone. How's everyone doing today? Last class before the spring break. I think we're all excited for a week break. Okay. So for those of you just kind of tuning in on Zoom, and for those of you, I mean, if you're watching this on YouTube, then you probably just caught the previous exchange. But problem 3 on OpenFOAM activity 1 did end up being a little bit more complicated than I anticipated, mostly because of the turbulence modeling variables. And so we're going to talk more about just changing that simulation type after the spring break in activity 2. But if you're still working on OpenFOAM activity 1, problem 3 is optional. Right. There are kind of simple ways that you can do it just to kind of get the activity done. Like for instance, you can basically just take the bottom wall and move it to the right with the same velocity as the top, right? So all that would entail was taking a boundary face from your fixed walls that specifies the bottom wall and move it into the grouping for the moving wall up here. So you can do that without changing anything for the turbulence parameters. So that's one thing you can do if you want to do problem 3. But for those of you that were trying to do something like make the right wall move, I think it's been a little bit of a struggle just because of the turbulence parameters. So I'll make problem 3 optional. You don't have to do that one. We'll definitely talk more about it after the spring break. But there are ways that you can do it. The longer winded version would be to actually change the simulation type to laminar. So this kind of outlines the steps a little bit to do that. Basically these ones right here. So you can do that as well. But since we're not going to get a chance to do it together, I'm just going to make problem 3 optional. Okay. Okay. All right. So that hopefully kind of clears that up. And so the plan for today is we're going to finish our lecture notes on the simple method. And so we have a little bit more of the derivation to go. And then we have one fairly lengthy example that we're going to do together. Okay. So the example that we're going to do today is very similar to the problems that you're going to be doing in homework 4. I know probably you guys are still working the open form activity. You haven't had a chance to look at homework 4, but the example today is very similar to that. Okay. All right, so that's the plan. Hopefully we get through everything. I think we'll get through everything before the spring break, just so we're not talking about simple when we come back. Okay. Any questions on anything before we begin? Okay. All right, so let's go ahead and pick up where we left off on the derivation. So I'm actually just going to scroll up. And so this should already be in your notes. And so, there's not too much to go by here. Okay. But basically, let me actually scroll all the way up here. Right. Remember, we're kind of dealing with this very unique issue with discretizing Navier-Stokes, right? So ultimately, we want to have a scheme where we can basically take Navier-Stokes and solve for the solution of both the velocity and the pressure at the same time. Okay. But the issue we're having is that the pressure term is kind of giving us a little bit of difficulty because, on the one hand, the pressure term does not show up in the continuity equation, which kind of makes things difficult to solve for it. But also it kind of leads to a very interesting problem called the checkerboard problem, where we have kind of, alternating cells here that may, have a certain solution. Okay. And the reason for that is because our solutions are decoupled. Okay, so we're kind of tackling kind of 2 problems at the same time. And the way we're doing it is through a method that we call the pressure correction equation. Okay. So how we got here was that, we took Navier-Stokes. So this is kind of a simple 1-dimensional version of Navier-Stokes. We integrated it over over a cell, just like we typically do in finite volumes. Okay. And we kind of make the concession where we basically said that, since we're only working on the momentum equation, we can only solve for one of either the velocity or the pressure, right? Because we can't solve for both at the same time, okay? And so the concession that we make is that, we're going to solve for the velocity first, right? And we're going to leave the pressure essentially fixed, okay? So we're basically working on an equation where our pressure remains fixed to what it was previously, okay? And we're going to solve for that velocity first, okay? Now, the caveat here is that, by solving for the velocity in this context, that velocity will not be completely correct, right? It'll be closer to being correct, but it's not 100% there because we've essentially neglected the pressure, okay? And the main way that we're going to kind of check and see if that velocity is correct or not is by checking mass conservation, right? So by doing this method, by basically solving for the velocity first without the pressure, we're basically saying that the velocities that we get are not going to be mass conserving. Okay. So we come up with this symbol, right? We're basically calling it U star, where U star is what we're going to call our updated velocity, but not our correct velocity. Okay. Okay. And then now our strategy is that now that we have this updated velocity, we want to apply a correction to it in order to get it into a mass conserving, right? And so what we're saying is that, if we take our updated velocity, we add to it some kind of velocity correction, that's going to give us our true velocity here that is not only correct, but also mass conserving, okay? And we're going to do the exact same thing with the pressure. So we're going to apply a pressure correction, okay? Okay, so that's just about where we left off. But, the last thing that we did was we basically took this idea or took these kind of equations here for our velocity and pressure correction and applied that directly to our continuity equation, okay? All right, and then we ended up with this kind of expression right here. Okay. And so the way to kind of interpret this equation here, this is essentially our conservation of mass, but we've kind of split it up into 2 sides. So on the left-hand side here, right? On the left-hand side here, these are our continuity terms that involve our velocity corrections. hence the prime symbol, right? So we have UE prime minus UW prime, okay? And everything on the right here involves our updated velocity, right? So that's the velocity that we obtain with the incorrect pressure, right? So what we're saying is that these velocities are not going to be mass conserved. Okay. And so because our updated velocities are not mass conserving, the right-hand side of this expression is going to be non-zero, right? Because so if our velocities were mass conserving, then the right-hand side would be zero because we take the inlet flow and we subtract the outlet flow, and so those should cancel out and become zero if we are perfectly mass conserving. But if they're non-zero, that means we have some error in our conservation of mass. Okay. Okay. All right, so let's take all that information and then let's kind of work on this equation from here. Okay. Our next step in this derivation is to basically we're going to come up with expressions and plug in for the velocity expressions on the left-hand side. Okay. Because remember, we can only solve for one thing at a time, so we can't solve for both velocities and pressure. So velocity has already had a term. So it's just like your children, right? Like Johnny can only play with one, only one kid can play with the toy at a time, right? So since we've already given velocity a term, let's solve for the pressure instead. So we're basically going to replace the velocities on the left-hand side with expressions that involve the pressure, and then we're going to use that to compute the pressure correction. Okay. Okay, so that's kind of the strategy there. Okay, and so the next step in this derivation is let's come up with an expression. And the way we're going to do that is we're going to use momentum. Okay, so we're going to use the momentum equation to plug in for the velocity corrections. Okay, and basically put our continuity equation in terms of pressures instead. Okay. All right, so let's go ahead and do that. So remember that we've already applied our finite volume method to our momentum equation, right? So after applying the finite volume method, okay. So I'm going to use kind of the vastly simplified version of our momentum equation that kind of just only has the linear coefficients. Okay. So just for the sake of time, right? So remember we kind of had this kind of very simplified form last time. The only difference now is that I'm going to apply the same finite volume method to our velocity corrections. Okay. Okay, and so doing so, we get AE multiplied by UE prime plus summation of AF UF prime is equal to minus VE partial P partial X prime. Right, so on the left-hand side, basically we have all of our velocities for all of our face values with some kind of coefficient in front. Those are what the A coefficients are, right? And on the right-hand side, we have just our pressure. But now we're doing everything in terms of the corrections, right? Because the corrections, they should also satisfy a momentum as well. Okay. All right, so next thing I'm going to do is I'm going to divide this entire equation by AE. Okay. And so essentially, we're going to take this momentum equation and solve it for just one of the velocities, okay? Specifically the velocity on the east face. Okay, so we do that, we get UE prime. Right. Actually, let me do two steps into one. Let's divide by this and solve for it. Okay. So that means all of the other U terms are going to move it over to the right-hand side. Okay. So we get UE prime is equal to minus, let's see, summation of AF divided by AE, UF prime, minus VE divided by AE, partial P, partial X prime. Okay. All right, so what we have from this expression here, this is something that we can plug back into our continuity equation, right? Right? Because remember, the goal of this part here is that we want to replace our velocity corrections in the continuity equation and put that in terms of the pressure corrections. Okay. Okay. All right, so I am going a little bit fast through this just because I do want to get to the example. I don't want to be talking about this again after spring break because I want to get more into open foam stuff. But just know that the lecture notes posted online does have a bit more of the steps, okay? But I do want to not really highlight the details of this so much just because I'm not going to be asking you to discretize Navier-Stokes. You know, even just the small part is there's still more to go. But I want you guys to really kind of appreciate just kind of the steps and the process that we need to do to get this. Okay. Okay, so plugging this back in, right? So just to kind of give you a sense here, we're plugging back in for these two highlighted quantities here, right? So everything else is going to be the same. Okay. And so we plug in for that, we get rho, right? So we're plugging in for UE prime here. So that is minus summation AF divided by AE, UF prime minus VE over AE, partial P, partial X prime times delta Y minus rho. Same thing for UW, right? And so UW here is going to be minus AF divided by AW, UF prime minus VF over AW, or excuse me, VE or VW, V for the west side, okay, times partial P, partial X prime, okay, is equal to our two non-mass conserving terms minus ME dot star plus MW dot star. Okay. Okay.
Does that have a delta Y as well?
Yes, it does. Thank you. All right, and so we've replaced essentially the main velocity corrections on that left-hand side, right? And so now we can basically solve this for the pressure, right? So we've kind of accomplished one of our main goals here was that we've taken our continuity equation, which previously did not have the pressure in it, and now we've plugged in for it so that now the pressure is here, right? And so now we can essentially take this equation here and use that to solve for the pressure equation, which is something that we couldn't do before, okay? And so the last step to this procedure here is basically to plug in for these two expressions here, because that's where the pressure is going to come in. And so essentially, we're going to use a finite difference method to plug in for these pressures. All right, and then we finally arrive at the pressure correction equation. Okay. And so the pressure correction equation, right? And so I'm going to leave all the pressure terms on the left-hand side. So on the left-hand side, we have a rho, minus rho, excuse me. So minus rho times VE divided by AE delta X times delta Y up top, okay? Times P E prime minus P C prime minus, there's the plus, two minuses cancel out. So rho BW delta Y divided by AW delta X EW PC prime minus PW prime, okay? All right, all this is equal to minus M dot E star plus M dot W star, okay? Plus the extra terms here that come from the velocity corrections here. So plus rho summation AF over AE UF prime delta Y, okay, minus rho summation AF over AW UF prime delta Y. Okay. Right. All right, so this right here, this is our pressure correction equation. Okay, and I know it's a mess. It's not even a fun expression to write here. But remember, you know, I'm not really concerned with the details of this derivation. I want you guys more to kind of just kind of appreciate kind of the process that we took to get. Okay, because this equation, you know, there's obviously a lot of work that came into this. But the main thing is that now this essentially is our continuity equation. But now it's in a form that we can actually use it to solve for pressure, which is kind of one of our main issues. Don't worry, we're not. I'm not going to ask you to actually solve this equation because that's kind of crazy. Okay. We are going to do a pressure correction, but we are going to do it in a very simplified way. But in order to do that example, you kind of have to understand kind of the process and the steps that we took to get there. Okay. All right. Any questions on this? Okay, good. Okay, and so now that we've kind of arrived at this pressure correction equation, we are finally ready to state the simple algorithm. Okay, so let me go ahead and zoom back in here. Okay. So remember, simple is an acronym, right? So simple stands for semi-implicit method for pressure linked equations, right? And it's really, you know, the pressure correction equation is kind of just one part of it. And so I'm going to list all the steps here, and then we'll actually apply to a very simple example. Okay, so step one. So step one to the simple algorithm is you have to start with an initial guess for your velocities and pressure. Okay. So essentially, our simple algorithm belongs to a class of algorithms that are called iterative methods. And so with iterative methods, you're basically going to be, iterating and solving and going through these steps multiple times. And so the starting point is that you need to have some kind of starting guess. Okay. Sometimes the starting guess matters a lot. Sometimes there are some algorithms where you have to kind of start relatively close to your solution. But there are some algorithms where you can start very far away and still be able to come back. Okay. Simple algorithm kind of falls in between those two. So if you're extremely far off, then simple is not going to work. But there is some robustness where you can have kind of a pretty far off guess and still kind of arrive at the correct answer. Okay, step 2. So step 2 is to solve for the updated velocity. Okay, so remember we gave the symbol U star, okay, using the momentum equation. Where remember the key to this is that we are holding the pressure constant. So the pressure is going to be basically going to be held constant at our initial case. Okay. Okay. Step 3. So after you solve for your updated velocities, right, we know that our new velocities here are not going to be mass conserving. They're going to be updated. So they're going to be more correct, but they're not going to satisfy continuity. Okay. So step 3 is to use results from part 2 to compute mass flow rates. Okay. So mass flow rate, remember, is going to be rho times U star times delta Y. Right, so that's going to go on the right-hand side of our pressure correction equation, right? So we basically need to know the error in our mass flow rates, right? And so that's essentially that's what's going to get it for us. Okay. Step 4 is to use the result from part 3, right? So that's the error in the mass flow rates and plug that into our pressure correction equation. Okay. And so what that's going to allow us to do is that's going to allow us to solve for the pressure correction. Right, so that's going to go as P prime. Then once you have the pressure corrections, then you can then use the pressure corrections to compute the velocity corrections, which you're going to use the momentum equation for. Okay, so use result from 4 and plug into momentum. Okay. So after step 5, you'll have both the pressure correction and the velocity correction. Okay. Okay. All right. Now that we have both the pressure correction and the velocity correction, step 6 is to actually apply them, right? And so basically we're going to compute our new velocity, which is going to be our updated velocity u star plus u prime, and our new pressure is going to be P, I guess it's star. We haven't used another symbol for it, plus P prime. Right, so you just basically take your old values of velocity and pressure and just add to it just to get their new values. Okay. All right, and then finally, step 7. All right. Once we apply our corrections, we need to check and see if we've converged. Okay. Okay. And so the beautiful thing about Navier-Stokes is because Navier-Stokes is a nonlinear equation, it's usually going to take us more than one try or more than one iteration to get this right. Okay. So the way we check convergence, typically we check our mass conservation. Okay. And so we check to see, if all the mass flow rates, if you add them all up, they should sum up to 0, right? That's mass conservation, or at least get you close to 0. Okay. Usually there's some threshold. So usually when you're writing computational code, it's very hard to get something that matches 0 exactly. So usually you're going to say, we're going to compute continuity, and we're going to say if the error is less than some small number, maybe 10 to the minus 3, then we say we've sufficiently converged. Okay. So if error is less than some threshold, usually around 10 to the minus 3, right? Then we can say we've converged. Right? If not, we could do this whole thing over again. And so if not, we basically repeat this entire process from step 2. Okay. So you go back and you kind of do the whole thing again, right? And so eventually, you keep doing this. And so, there's a lot of kind of proof and stuff that we're skipping over here, but, you can prove that this simple algorithm is a convergent algorithm. And so you do this enough, you should get a solution that's well converged, that's mass conserving, that satisfies momentum and continuity. Okay. All right. So it took a lot of work to get here, essentially, 1 lecture and a half. But that's kind of the beauty of this simple algorithm. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So like I mentioned, we're not going to apply the simple algorithm to Navier-Stokes, or I'm not going to make you guys do it. That's kind of crazy. But there is a way to apply a simplified version of this to, essentially very simple pipe flow problems. So let's go ahead and look at that. Okay, so let's look at flow in the following pipe network. Okay, and so we have kind of this fairly complicated piping network here. So let me go ahead and draw it out. So each line here is going to represent a pipe. Okay. So this here is going to be node 1. This is node 2, 3, 4, 5, 6, 7, 8, and 9. Okay. Okay. And so we have basically a pipe flow here where we have several different junctions, right? And so there's a junction at node 3 where we have flow coming in from 1, 2, and 4. It's going to go to 6, right? And then so on and so forth, right? So I'm going to draw some arrows here. So the arrows are going to indicate the direction of the flow, right? Right, so let's say that we're going to assume that flow, the water is going to flow from point 1 or node 1 to node 3, okay? Flow is going to go from node 3 to node 2, from node 4 to node 3, right? From node 3 to node 6, from node 6 to node 5, from node 7 to node 6, from node 6 to node 8, and from node 9 to node 8, just like that, okay? Okay. All right, and then in each of the pipes, right, we're going to compute the mass flow rate in each of the pipes, right? So the first pipe on the left here, we'll call that pipe A, and so then we're going to have the mass flow rate through pipe A. This pipe we're going to call pipe B. Okay. I'm going to use a different color just because it's just to make it stand out. There's a lot going on in this figure. Okay, so pipe A is going to be the pipe that connects node 1 and node 3. Pipe B is going to be the pipe that connects node 3 and node 2. Pipe C is going to connect 3 and 4. Pipe D is going to connect 3 and 6. Pipe E is going to connect 6 and 5. Pipe F is going to connect 7 and 6. We have pipe G that's going to connect nodes 6 and 8. And we have pipe 8 that's going to connect 9 and 8. Okay. And then we have one more pipe that's going to lead out from pipe for nodes 8. Okay. But that's essentially going to be our outlet. All right. And then in addition to this, we are going to define the pressures at each of the nodes. Okay. Okay, so at node 1 on the left-hand side, we're going to have a pressure P1 of 400. Node 2, we're going to have a pressure of 350. Node 4, we're going to have a pressure of 50. Node 5, we're going to have pressure of 300. Node 7, we're going to have a pressure of 800. Node 9, we're going to have a pressure of 200. Okay. And then the pressures on the interior, so pressures 3, 6, and 8, those are going to be our unknowns. So that's essentially what we're going to be solving for. So you have P3, P6, and P8. Interior pressures. So we're going to be using our simple method to essentially solve for those pressures. Okay. Okay, and then last piece of information, I forgot to mention it here. We do know the flow rate out, and so M dot I is actually going to be 50. Okay. All right, so there's a lot going on, so I'll give you guys kind of a second to make sure you write down all the numbers there. Okay. Okay. But as you're writing it down, we've basically set up a system where we can apply our simple algorithm. Because remember, so one thing I forgot to mention today, that remember, one of the requirements for simple is that we have a staggered velocity and pressure. Okay. We have that here, right? And so if you look at our system here, our pressures are defined at the nodes of the system, right? And then in between the nodes, we've defined the mass flow rate. So the mass flow rate is going to be kind of our surrogate for the velocity. Okay. So in other words, we have velocities and pressures defined at different locations in our system. So this sets up kind of a very perfect staggered grid. And so it's kind of the perfect way for us to apply our simple algorithm. Okay. All right, so that's kind of the goal here, right? And so we're going to use this kind of relatively simple example to illustrate how the simple algorithm works. And luckily for us, since this is a relatively simple case, it is going to be linear, and so we're going to get the solution just one iteration. So it's not like we have to repeat it over and over. Okay, any questions so far on the setup? The setup's not done. We do need a few more pieces of information, but I know this was kind of a lot to kind of take in first. Yes.
So the reason it's a staggered grid is because some of the values, the pressures are at the nodes
Yes.
and the velocities between them.
Exactly. Yeah. Yeah. So remember the key for the staggered grid is that your velocities and pressures are not defined at the same location. Yeah. So in finite volumes, remember we define the pressure at the cell centers, but then the velocity we define at the cell bases. And so this is kind of an ode to them. Okay. All right. So let's kind of complete the setup here. So the other thing that we need is we need the diameters of all these pipes. Okay. Okay. So we have the diameter of pipe A, diameter of pipe B, diameter of pipe C, diameter of pipe D. Let's see. 2, 6. Okay. Diameter of pipe E, diameter of pipe F, diameter of pipe G, and diameter of pipe H. Okay. Okay. All right. And so the diameter of pipe A here is going to be 0.5. Diameter of pipe B is going to be 0.4. Diameter of pipe C is 0.3. Diameter of pipe D is 0.19. Diameter of pipe E is 0.3. Pipe F is going to be 0.4. Pipe G is 0.1875. And for pipe H, it's 0.35. Okay. All right, and then the last thing that we need here is we need a way to relate the mass flow rates and the pressure, right? And so essentially we need our momentum equation here. Okay. Because we're not going to use Navier-Stokes, right? Because Navier-Stokes is a little bit too crazy to use. So we're going to work with the modified momentum equation. Okay. And so our modified momentum equation is going to say that mass flow rate in a given pipe is equal to the diameter multiplied by the difference in pressure between the nodes. Okay. Okay, so it's just going to be simple, just D times delta P, where delta P is the pressure, because remember, our mass flow rates are defined in between the nodes. So delta P there is just going to be the difference between the upstream node and the downstream. Okay. So a lot is set up for the problem, right? But I promise the problem itself is more straightforward. There's just a lot of numbers for this problem. Okay. All right, so let's go ahead and apply our simple algorithm to basically solve for these pressures here. Okay, and then along the way, we're also going to solve for the mass flow rates as well. Okay. Okay. Apply simple. Okay. All right, so let's go through our steps of the simple algorithm and let's see how they apply here. Okay. Okay, so step one. Step one is we need to start with an initial guess for all unknown quantities in the system. And so all of the unknown quantities in the system are going to be the internal pressures, right? So P3, P6, and P8 are unknown, right? So we need to have an initial guess for those. And once we have those, we can then use those to compute m dot based on our momentum equation that we have up there, okay? Okay, so for this problem, let's start with our initial guesses for pressure, right? So let's say P3 at n, right? Our initial guess for P3 is going to be 300. Okay. For P6, our initial guess is going to be 200. And then for P8, our initial guess is 120. Okay. So does it matter in this case what your initial guesses are? Probably not, because it's a linear problem, so you can actually start fairly far. But for this problem, we'll start with these initial guesses here. Okay. Okay. Now that we have our initial guesses for pressure, let's go ahead and compute our initial flow rates. Okay. Which I guess technically is step 2 of the well, for our case, since we're doing a simplified case, this is technically steps 2 and 3, right? Because we're not computing velocities, we're just jumping straight to the mass flow rates. Okay, all right, so we compute our mass flow rates. So let's do each one. Okay, so we have m dot a, right? And since this is going to be an intermediate flow rate here, we're going to give it a star. Okay. Okay. So when you're computing the flow rates in these problems, you have to be a little bit careful because you want to make sure that you put the pressures in the right order, right? So the mass flow rate is going to be the diameter of pipe A multiplied by the difference in pressure. Okay. Now this difference in pressure, we can have two different ways to do this, right? And so we go back to our figure here, we see that pipe A is between nodes 1 and 3, right? And so for delta P here, we can have either P1 minus P3 or P3 minus P1, okay? Right, and it does matter. It does matter which one that you pick. So you want to make sure you pick the right one, okay? Okay, and so the way that you pick this is you basically go off the convention that you've defined in your figure, okay? And so for this particular figure, we can see that we've drawn an arrow, right? We've drawn an arrow that goes from node 1 to node 3, okay? And so by doing so, we're making the assumption that flow is going to go from pressure P1 to P3, okay? And so because of that, right, the delta P that we pick is going to be this one right here. So based on direction in figure, flow goes okay. So you want to make sure that you kind of obey the arrows that's drawn for you. Okay. Now, not every time are you going to have arrows drawn on your figures, right? And so it's okay to draw those arrows yourself if you're missing. And don't worry too much about getting the direction right or wrong. Sometimes you can't really tell which direction the flow is going to go. If you get the direction wrong, you're just going to get a negative number for m dot, and that's totally fine. The only thing you have to make sure is that just whichever direction that you pick, you want to make sure you're consistent with that direction throughout the entire problem. Okay. So I always recommend that, if your problem has arrows, just follow them for the problem. But if the problem does not have arrows, you can draw them in yourself. Okay. Okay. But since we know the direction here, we're going to go from 1 to 3. This is going to be dA. multiplied by P1 minus P3. Okay. P3, and we denote that P3 now is just a guess, right? So P3 is just P3N. And so we go ahead and multiply that through. We get M dot through pipe A is going to be 50. Okay, so I'm going to do the exact same thing for all the other pipes, and I am going to go a little bit quickly just to make sure that we finish this example here. Okay, so M dot B is going to be dB multiplied by P3N minus P2 is equal to minus 20. Okay. All right, so this is a good example. So, the fact that we got a negative flow rate through pipe B, right? That tells us that the direction that we picked for pipe B is actually incorrect. Okay. And so that means that the flow in this case is actually going to go from node 2 to node 3, which makes sense because our pressure P2 is greater than our initial guess for P. Okay. But don't go back and change the direction. It's just something to note here. The flow in this case is similar to current, if you remember that from your circuits course, right? A negative current just means that the current just flows in the opposite direction, which is not that. Okay. Next, we have M dot C. We have DC, and this is P4 minus P3N. Okay. Okay. This gives us a minus 75. Okay. And all these are star, excuse me. We need to have stars on these. M dot D is going to be D in pipe D, P3N minus P6N. Right, this gives us 19. Okay. Okay, pipe E, we have DE times P6N minus P5. Right, this is going to give us minus 30. Okay. M dot F star is equal to DF P7 minus P6 N is equal to minus 48. Okay. Next, we have M dot G. So M dot G is DG times P6 N minus P8 N. That's going to give us 15. And then M dot H is equal to DH P9 minus P8 N. Okay. It's equal to 28. Okay, so a lot of numbers in this example, so I apologize, it's a lot of writing. But I did want to give you something that's fairly complicated for an example, so that when you go to do the homework, when you go to do the exam, you have at least a reference here where it's fairly well done out, and it's a fairly complicated problem, just so everything else is hopefully going to be easier from here. Right? Okay, all right. Good. I know probably people are still writing it down, but are there any questions on this so far? Okay, good. Okay, so now that we have these mass flow rates, we can then use them to check continuity, right? So these mass flow rates, remember, these are intermediate quantities, so they're not expected to satisfy mass conservation. So our next step in our simple algorithm is we're going to check mass conservation, right? Specifically, we're going to check mass conservation at the interior nodes, because those are the nodes where we have some uncertainty, right? We don't know the pressure there. Okay. All right, and so let's go ahead and sum up basically all those mass flow rates. Okay. Okay. So for node 3, right, we're basically going to sum up all of the mass flow rates coming in and all the mass flow rates going out. Okay. Okay, so for node 3 here, we can see that we have 4 contributions. We have mass flow rate A, mass flow rate B, C, and then D. Okay. Now, some of these mass flow rates, according to these arrows, are going into the node, and then some mass flow rates are leaving the node, okay, just based on our arrows. Okay, so let's do node 3 first. All right, so for node 3, so the convention that we use that if the mass flow rate is entering the node, we use a minus sign. So you have a minus m dot A star minus m dot C star. Okay. So these two mass flow rates are entering the node. Okay. And then for mass flow rates that are leaving the node, we use a positive number. Okay. So plus m dot B star plus m dot D star. Okay, so once again, pay attention to the directions and make sure that you're consistent throughout the entire problem. Okay, and so let's go ahead and sum up all of these mass flow rates. So we just painstakingly computed them in the previous step, right? And so we take m dot A star minus m dot A star minus m dot C star plus m dot B star plus m dot D star, okay? And the result for that is 24. So we get something that's non-zero, which is expected, right? And so if these velocities or these mass flow rates were mass conserving, then everything added up to the node should be 0. Okay. But the fact that they're not means that our velocity field or our mass flow rates here are not mass conserving. Okay, so let's do the same thing for the other nodes. Okay, so we're going to have node 6. Okay, so for node 6, we have minus m dot D star minus m dot F star plus m dot E star plus m dot G star. Okay. So this has the same convention as above, right? So any mass flow rates entering the node, we're going to put a minus sign there. Any mass flow rates leaving the node, we're going to put a plus sign. Okay. All right, so we add all these up and we get 14. So once again, we get something that's non-zero, which which makes sense because our mass flow rates here are not mass conserving just yet. And then we have the same thing for node 8, right? So for node 8, thankfully, we only have 3 contributions here. So we have a minus m dot G star minus m dot H star. And then we have only one contribution that's leaving, which is m dot I star. Okay. And so this gives us 7. Okay. All right, and so we have a system here where we're not mass conserving. So this we do need to correct these mass flow rates, and we do need to correct our pressures as well. Okay, so we've computed our intermediate mass flow rates. We've checked continuity. We know that we're not mass conserving. Next step in our simple algorithm is to compute our pressure corrections. Okay, so that's going to be step 4. Okay. So we need to basically take our continuity equation, take our momentum equation, and use those to derive equations for our pressure corrections. Okay. All right. So the way we're going to do this is that, we're basically going to say for every node, okay, we have the following relationship. So basically, if we sum up all the mass flow rates, both the updated one and the corrected one, okay, they should equal to 0, right? Right. So basically, we apply a correction to our mass flow rates. That's going to correct them, and then mass conservation is going to be satisfied at that point. Okay. Okay. So we've already computed these, right? Right. So we computed these in the previous step. We now need to get expressions for these, right? And to do that, we're going to use our momentum equation, but we're only going to use our corrected pressures. Okay. So unfortunately, this is another step with a lot of writing. But basically, we're going to take the expressions that we did for step 2, right? So basically, all of these expressions here, right? And we're going to replace everything that's unknown, right? So anywhere we see P3, P6, or P8, and we're going to replace that with the replacement with the correction pressure, okay? But all the other pressures that we already know, right? So all the pressures that are known already, so P1, P2, P4, P7, P5, P9, right? Those don't need correcting because we already know those values. So we already know P, P1, P2, P4, P4, P5, P7, and P9, right? And so for these pressures that we already know, then there's no correction is needed. Okay. So we only need to apply corrections to the pressures that are unknown to us, right? So only the pressures on the interior. Okay. And so for these problems, I will always tell you which pressures are unknown, and those are the ones you bet correction. Okay. If it's not indicated there, then you can basically assume that that pressure is no. Okay. Which is great because that cuts down the number of unknowns in our system to only 3 as opposed to 9. So 9 would be a little bit crazy. Okay. Okay. So we're going to get basically expressions for our corrected mass flow rates that only involve our correct pressures. Okay. So for instance, m dot a prime. Okay. So m dot a, right, normally is the difference between P1 and P3, right? But P1 is already known, right? And so our corrected m dot a is just going to be minus dA multiplied by P3 prime. Okay? So we're only going to include the contribution from the corrected pressure. Okay, and then let's do the same thing for all of the other types here, right? So m dot b prime is equal to dB multiplied by P3 prime, okay? If you're wondering why the first one's positive, the second one's negative, right? And so just to kind of remind you, m dot A, right, is dA multiplied by P1 minus P3, right? Because remember, P1 is known, right? So since P1 is known, we don't need to correct it. And so the only term that needs correcting is P3 prime, okay? Similarly for m dot B, right? So m dot B is dB multiplied by P3 minus P2, right? P2 is known, so we don't need to correct it. And so our correction equation is just dB times P3 prime. Okay, and then m dot C prime, this is going to be A minus DC times P3 prime. Okay. M dot D prime, this is equal to DD P3 prime minus P6 prime. Okay, it's our first equation here with multiple correction pressures. M dot E prime is DE times P6 prime. Okay. M dot F is minus DF times P6 prime. M dot G prime is equal to DG times P6 prime minus P8 prime. And then finally, M dot H prime is minus DH P8 prime. Okay. All right. Maybe you should have picked a simpler problem for this. Okay, but essentially, we have essentially, 8 expressions here, right? And they all involve our corrected pressures, okay? Our next step, right? Step 5 is basically to apply this to our pressure correction equation, okay? Actually, not yet. So this is still step 4, okay? Right, and so now that we've computed all of these m dots primes, right? We're going to plug it into this expression up here. Okay. Okay. All right, so our continuity equation is basically the summation along each node, right, of m dot star, right? So m dot star, those were the non-conserving mass flow rates that we computed earlier in step 2, plus the m dot primes, which we had just computed up here, and all that's going to be equal to 0, okay? So let's modify this equation. So let's go ahead and move this term over to the right-hand side of the equation, okay? And so we get summation along each node of the m dot primes. So basically all the corrected mass flow rates that are entering the node is equal to minus summation of the incorrect mass flow rates m dot star. Okay. Okay. So we're basically going to apply this equation to each node. Okay. All right, so let's go ahead and do that. So let's apply this to node 3. Okay. Because that is where our first interior node is, right? And so on the left-hand side, we're going to have minus m dot A prime minus m dot C prime plus m dot b prime plus m dot d prime is equal to m dot a star plus m dot c star minus m dot b star minus m dot d star. Okay. So right-hand side of this expression, remember, those are our updated velocities. So we computed these in step 2. Right? So we can just go ahead and plug in for those. And so on the right-hand side here, we basically get the negative of what we got in step 2, right? Right. And so, for node 2, we got, or for node 3, we got a positive 24. And so on the right-hand side here, this is going to be a minus 24. Right? And then on the left-hand side here, we just computed all of these up here in step 4. Okay. All right. And so for this one, we get a minus m dot a prime, right? So m dot a prime is a minus dA times P3 prime. Okay. And if we get a minus sign for that, that is equal to positive dA P3 prime. Okay. We get a minus m dot c prime. And so that's going to give us a positive d sub dc P3 prime. We have a positive m dot b prime. So positive m dot b prime, that is a dB. P3 prime. Okay. And then finally, we have m dot d prime. And so that is d times P3 prime minus P6 prime. All right. All right, so all the diameters here are known. The p primes are not known, so those are still unknowns in the equation. But what we're able to get from this is basically an algebraic equation that we can use to solve for P3 and P6 prime when combined with the other nodes. Okay, and so we plug in for all the diameters we get 1.39 P3 prime, okay, minus 0.19 P6 prime. All this is equal to minus 24. Okay. So in the interest of time, we're going to kind of, I do want to get to the end of this example because this is kind of what the homework's all about, right? So let's apply the same method to node 6 and 8. Okay. And so doing so is going to give us two more algebraic equations that we can solve for P3, P6, and P8. Okay. So for node 6, node 6, we get the following equation, 1.0775 P6 prime minus 0.1875 P8 prime is equal to minus 14. Okay. And then for node 8, we get minus 0.1875 P6 prime plus 0.5375 P8 prime is equal to minus 7. All right, good. And so we solve these three equations, right? And so you know we can solve these three equations at the same time for P6, P3, and P8 prime. Okay. Right. So you know, for a linear system of equations like this, if you are savvy with the linear algebra, you can solve this by hand. Or if you're lazy like me, you can just punch this into a matrix solver like MATLAB or your calculator, right? And what we get is P3 prime is equal to minus 20. P6 prime is equal to minus 20. And P8 prime is equal to minus 20. Okay. So it just kind of worked out for this problem where all of our pressure were just off by 20. But in reality, you know, for a normal problem, your pressure corrections are not going to be all the same like this. Okay. All right, and so last steps here is just to apply our corrections. Okay. And so P3, the true value, is going to be P3, our initial value, plus P3 prime. Okay. P6 is going to be P6n plus P6 prime, and P8 is equal to P8n plus P8 prime. Okay. Okay. All right. And so since we were just off by 20 on each one, right? Let's see, where our initial pressure is. So P3 is going to be 280, P6 is going to be 180, and P8 is going to be 100. Okay. Okay. All right, and then last step in this problem that we unfortunately ran out of time for is that now that we have our pressure corrections, we can then correct our mass flow rates as well. Okay, so last step. Apply corrections to mass flow rates. Okay. Because now that we have all the P primes here, we can go up here and, you know, plug in for, you know, our M dot primes here. So M dot A through H. Okay. And then once we have our corrected mass flow rates, we can then confirm that continuity is satisfied. Okay. Okay. So unfortunately, you know, you're going to have to take my word for it that that continuity is satisfied here, right? Since we are working with a linearized version of Navier-Stokes, there's no need for iteration. We kind of just get it in one step. But it is something good for you to go back and confirm, especially because you're going to need to do this on the homework as well. Okay. All right. Any final questions before we wrap it up here? Okay, all right. So I apologize for going over. That was a little bit more intensive than I thought it was going to be, but that should give you everything you need to do for the homework. So thank you guys for coming today. Thank you guys for sticking around a little bit. I hope you guys have a good, restful spring break, and I will see you on the other side. Thanks. Have a good spring break, guys.
Good break, that's-
You too, David.